When you do your first statistical test, you may get the impression that doing statistics is complicated. There are so many variables and values, a level of significance, a p-value, a t-value, an f-value, and much more. Here in this video, we want to show, however, that the principle of statistical testing is actually relatively simple. Statistical tests are generally based on two steps. First, the calculation of a so-called test statistic, and second, the comparison of this test statistic with the threshold to decide if a difference is random or not, or in other words, if a difference is statistically significant or not. Let's have a look at step 1. A test statistic is a value calculated using our data according to a formula which somebody invented or which was derived based on mathematical considerations. Let's have a look at students' t-test as an example, which is used to compare two groups. A typical example of using t-test would be the comparison of body weight in adults, for example, to answer the question if there is a difference between the weight of women and men. Now, the first step of this test is the calculation of a test statistic, which in the case of the student's t-test is called a t-statistic or simply a t-value. A formula is used which has been based on the assumption that data are normally distributed. We use this formula to calculate a t-value from our measured data. We don't need to worry about the details of the formula now. To understand the principle of a statistical test, it is enough to know that the test statistic is somehow calculated using a formula. If we look at another test, for example, Mann-Whitney-U test, then the name of the test statistic is different and another formula is used, but the main principle is the same. We calculate a test statistic. For Mann-Whitney-U test, the test statistic is not called T, but it's called U statistic, as you may have expected, since we are talking about Mann-Whitney-U test. Let's see another example, the F-test. The statistic for the F-test is called F-statistic, and this is the formula. So what do we do with this test statistic calculated with our data and using a formula? The key idea of the next step is the following. Let's consider we take two samples from the same data pool, or as a statistician would say, from the same population. Then there should not be a difference between these two samples. Of course, when we pick a limited sample, for example 10 random values from the same pool, there will always be some variation by chance, or a statistician would say some stochastic variation. But overall, we should obtain two very similar samples, with a similar mean value and a similar standard deviation. From these two samples, we can now calculate our t-statistic. Now this t-statistic describes a situation where there is no difference between the two samples. At least we know they are taken from the same population, so they should be similar. Now we can repeat the whole process and take another two samples and calculate t. And then we repeat the whole process again and again. After repeating this process many times, we have obtained a large number of t-values, all describing a situation where there is no difference between two samples. If we plot these t-values now into a graph, we can see how they are distributed. On the x-axis of this graph, we see the value of the test statistic that we obtained from our calculations. On the y-axis, we see how often a value occurred, that is, the probability of observing a given t-value. For example, a t-value from the center of the distribution was observed more often, that means it has a higher probability. A value from the tails of the distribution on the left or on the right was observed only rarely, it has a low probability. So this so-called t-distribution represents t-values which were all obtained when there was no difference between two samples. Now, how can we perform an actual statistical test? Well, we take the samples for which we want to know if there is a difference or not, and then calculate a t-value. Imagine we had obtained the following t-value located near the left tail of the distribution. How can we decide if the observed difference between the two groups is random or not? That is, if the difference is statistically significant. Well, the question is, how certain do we want to be that the difference is not random? Typically, we want to be quite certain. That means we only want to accept that the difference is not random when we are very, very sure. More exactly, 95% sure. This is why we usually use a level of significance of alpha equal to 0.05. Hence we accept that the difference is statistically significant only if the risk for error is 5%, which is expressed by the level of significance of 0.05. Now the t-distribution comes into play again. We can look at the x-axis and try to find the point where 95% of t-values are higher and 5% are lower. This is illustrated in the graph with the red line. This line represents a threshold with which we can compare our test statistic t, which we calculated from our two samples, from which we wanted to know if there is a difference or not. Since this t-value is lower than the threshold, we can conclude that we have a significant difference between the two groups. We could also express this in different ways. For example, we can be more than 95% sure that there is a difference between our samples. Or, the probability to observe a t-value from two samples which are not different is lower than 5%. Maybe this latter sentence also helps to understand the way how statisticians think. We actually started building a t-distribution which describes the case where there was no difference between our samples. This was our hypothesis, in statistical terms, our null hypothesis. And now, when comparing the t-value from our actual statistical test, we reject this hypothesis. In summary, statistical tests follow two steps. First, the calculation of a test statistic using our data and a formula. And second, the comparison of this test statistic with a threshold value using the distribution of the respective statistical test. While this is a correct description of how statistical tests work, there is something we didn't mention so far to keep things simple. What we actually did was a one-sided test. A one-sided test is a test where we only want to know if one sample is on average lower than the other. For example, we want to know if one group is heavier than the other. Another word for one-sided test is one-tail test, and this term refers to the distribution where we only looked at one tail. Now for two-sided tests or two-tailed tests, the principle is the same, but now we have two thresholds, one on the left and one on the right. Between the two thresholds, we have again 95% of t-values. So the level of significance still is 5% or 0.05. But now we reject the hypothesis, no difference between the two groups, either if our test statistic is below the lower threshold or if it is above the upper threshold. In this case here, we can see that the red arrow, our t-value, is still below the lower threshold. Hence we still conclude that there is a statistically significant difference between the two groups. So this is the relatively simple principle of statistical tests. We first calculate the test statistic, and then we compare this value with the threshold of the distribution of the test statistic. This distribution describes all values of the test statistic when there is no difference between samples. For two-sided tests, we use two thresholds instead of one.